Welcome back to 30 Days of Physics with Miss B, and we're moving right along with sound waves. Ever wondered if sound could actually break glass? Or why you could hear someone calling you from around the corner? Maybe after this lesson, you will be able to answer those questions. So let's get right to it. Sound travels to our ears via waves. They are produced by mechanical vibration, and these waves are referred to as progressive longitudinal waves, which travel best in solids. Sound waves require matter to travel, hence, it is not able to travel within a vacuum. Matter is any and everything around us, which takes up space. Matter is made up of particles. These particles may be atoms, ions, or molecules. Vacuums do not contain matter because it is airless. Sound waves are able to travel by vibrating particles. The closer in proximity these particles are, the more efficiently sound energy is carried. A sound wave is a series of compressions and rarefactions. Compressions are regions of high pressures, while rarefactions are regions of low pressure. Compressions are comparable to crests, as are rarefactions to troughs. Note the progressive transverse wave superposed upon a progressive longitudinal wave. Sound waves may be simulated via the use of a slinky or a spring. The loudness of sound depends on the amplitude of the sound wave. A large amplitude produces a loud sound, while a small amplitude produces a soft sound. The pitch of sound depends on the frequency of the sound wave. A greater frequency produces a higher pitch, while less frequency produces a lower pitch. Mathematically expressed, frequency is equal to the speed of the wave divided by the wavelength of the wave, where frequency is measured in per seconds and velocity is measured in meters per second, and lambda or wavelength is measured in meters. A frequency below 20 Hz is referred to as infrasound, while a frequency above 20,000 Hz is referred to as ultrasound. Frequencies between 20 Hz and 20,000 Hz are referred to as audible range of the average human. Old age reduces the upper limit to 16,000 Hz, which often results in drooping ears as we get older. It is a natural adaptation our body conforms to in order to enable more sound waves to enter the ear as efficiently as possible. Ultrasound is used in communication, measuring distance, medicine, industries, and cleaning. Sound waves reflect, refract, diffract, and interfere. An echo is an example of reflection of a sound. Sound waves bounce off of smooth, hard surfaces. An echo is produced in large or small open spaces that are barely populated but have high walls or surfaces. Similar to the behavior of a rubber ball bouncing off of a surface, the direction of sound changes after it hits a smooth, hard surface. Echoes can be used to determine distance, for example, the depth of an ocean floor or the distance of a thundercloud. Another useful equation for determining distance of an object via the use of sound is speed of sound equal to twice the distance traveled divided by t. Now you multiply distance by 2 because an echo has to leave your ear, travel to the surface, and come back to your ear. So it would have traveled the distance twice. So you have to account for that. Where v is equal to speed of sound in ear, 330 meters per second, d is equal to distance in meters, and t is equal to time in seconds. Sound waves refract or bend most at night when the temperature is cooler. As the cool, denser air falls, the warmer air rises due to expansion. Sound waves traveling in an upward direction will travel faster because hotter particles possess more kinetic energy than cooler particles. It is these particles that enable sound to travel faster at night than in the daytime. Sound waves diffract or spread out. Diffraction is the spreading of a wave as it passes an edge or goes through a gap. This explains why you can hear somebody around a corner or in another room. Speed, wavelength, frequency, and period does not change during diffraction. Sound waves interfere with each other. Interference involves two or more waves coming into contact with each other to produce either a larger amplitude, known as constructive interference, or none at all, which is known as destructive interference. Constructive interference can occur when two crests or two troughs come into contact with each other to produce a larger amplitude. Destructive interference can occur when a crest and a trough come into contact with each other, cancelling each other out. In this picture, crests are the curved lines while the spaces in between them represent the troughs. Examples of destructive interference are the green dots. That is where crests and troughs meet. Constructive interference involving two crests meeting is represented by pink dots, while constructive interference where trough and trough meets is represented by white dots. So back to these questions. Can sound actually break glass? And why could you hear someone calling you from around the corner? Yes, sound can break glass depending on some factors. A, the quality of the glass, B, the loudness of the sound, and C, the frequency of the sound. Sound is a progressive longitudinal wave. Longitudinal waves are composed of regions of high pressure and low pressure. Once enough pressure is exerted upon glass and it overcomes the strength of the glass, then it will shatter. Remember, speed of sound is equal to the product of frequency and wavelength. Hence, increasing the frequency greatly can affect the speed of sound. Very loud, high-frequency sounds will shatter glass because the sound wave is hitting the glass more frequently, complemented by a very large force due to its amplitude. Why could you hear someone calling you from around the corner? You are able to hear around corners because of a natural phenomenon referred to as diffraction. Diffraction is the spreading of waves after they have passed through a gap. These waves spread generously so that you can hear around corners. Alright guys, I'd like to thank you for watching another episode of 30 Days of Physics with Miss B. See you around for the 22nd day. Bye!